Thank you. This is Eugen and I'm Martin. And the reason we are here today is for a very simple fact, and that is when we are talking about 3D computer vision, and with that we mean that computers try to perceive the real world, the physical world, then the challenges that we are facing with the technology is very similar to what web people are facing. It starts with the perception part, meaning the data gathering of the. That is really a big challenge, as we will see, and the models and the data that we collect by using 3D perception technology, they are extremely large. And what is even a bigger problem is not only just the capturing of the data, but actually making sense of it. With sense meaning some kind of understanding what is being captured. And last but not least, visualizing all this 3D data is also a big challenge. But first of all, why should you care about 3D technology, which I think is one of the most important parts to realize whenever you start to be interested in a new technology. I remember the time when I had a desktop computer, and this computer was not connected with any other computer. And only recently we really started to connect these systems with each other. From a technological standpoint, the World Wide Web is not really new. But the interesting thing about the World Wide Web is, as soon as you start to connect machines together, the sum is much greater than the individual parts that make up the World Wide Web. And really the value lies in connecting different realms, being computers, together and forming the World Wide Web. Now, when we are talking about modern devices like smartphones or any kind of mobile device, we are now facing a very similar situation where this technology is now being started to be connected to a new realm. But this time it is not the digital realm, if you will, but the physical world through 3D sensoring. And this is really a big shift when it comes to the advancement of technology. I don't know what the next big thing will be with regard to these mobile devices and perception of the physical world, but I'm pretty sure that the effect on society and technology will be very similar in size and impact in general. So what is 3D technology being used for at this point already? For instance, there's a startup called Kiva Systems. They were bought by Amazon just some years ago, and as you can see, these little orange things at the bottom, these are autonomous systems who bring the individual goods that Amazon has in its warehouses to the people packaging it. There's another startup called Local Motors, and they are really into autonomous driving and how you can use 3D perception technology to have a car driven by itself, so to say. There are also startups and companies using 3D technology for inspection and maintenance. For instance, here to read regions which are really hard to reach for humans, or even in mining to drive these really big trucks. They are already being driven autonomously. And how to achieve this through 3D technology is actually not a super new thing, if you will, especially from a consumer perspective. In 2010, Microsoft Kinect was introduced to the market, featuring a 3-megapixel regular camera and a depth sensor. And the cool thing, of course, was with Kinect, which I guess plenty of you here already have used, is that that you have a completely different way to interact with a gaming console through Kinect. And now what is remarkable to me in just 5 years, I mean, the Kinect required an external power supply because it took so many power that the USB bus wasn't enough to power it. Now there's Project Tango from Google, and just within 5 years, they have basically shrink-wrapped the Microsoft Kinect technology into a mobile device, a phablet to be precise. And but both these devices, they generally only work indoor as far as we can tell for the Project Tango part. There's also, of course, technology that can be used outside, and it's one where Eugen actually is working on, and it is called Integrated Positioning System from the German Space Agency. And you can probably see this blue thing on the helmet right over here. This is the Integrated Positioning System, and it uses 2 cameras to perceive the world in 3D. and of course employs various other sensors. The key thing to take with here is that because of these different sensors that it uses, namely just regular camera technology, basically, it can not only be used indoor, as in case with Kinect, but also outdoor. But you probably have noticed that all of these devices have basically more than one sensor to grasp what's going on in the physical world. And this is for a good reason. Namely, we as humans, we have extremely sophisticated visual system, if you will. And just by looking at a two-dimensional picture like this one, you can get the physical dimensions in a certain way, at least. But when we are really just considering what a computer would see, well, the computer would basically just get a two-dimensional picture, literally, of the world, and would not have enough information to really get the third dimension, so to say, the depth. So to visualize what is missing in this picture, although we kind of grasp it as human beings, is being depicted in the second picture titled Depth Map. Here, the white parts in the image are the parts of the image of the left side, which are nearer to the camera. So the darker the color, the more away from the perspective of the camera is the individual pixel. And the reason I come up with this is to understand basically the basic technology and the basic things for the second part of the talk. And because when you combine this information that is being visualized in both images into one, you get something that is called a 3D point cloud. And this is basically just the extension of a two-dimensional image with a third dimension, namely the depth. But again, you can probably see certain issues arising. There's a very white part right over here. And this is one of the key things to take with here, that even though we have a two-dimensional picture that is being added a third dimension, it doesn't mean that the image that we get from the surrounding is complete. So everything that is white over there in the rightmost picture is basically data that is missing, where we know nothing about. Oh, this is important to understand when we come to this technology. Of course, the image that you just saw and the depth information, this is what you can get if you use sensors like we just described in terms of Kinect or of the integrated positioning system. When you are photographing a static thing, like for instance, what you can see over there, you can actually derive a 3D model just by taking multiple images from different perspectives. And this is being briefly described here. So just by having the same thing being photographed from different angles, we can deduce a 3D model of the thing, which is, I think, quite a remarkable achievement. So the talk is titled Data Challenges. And the thing about 3D in general is that we are talking really about a lot of data, right? So for instance, when we have a 9 megapixel image with 8-bit color, and 16-bit depth, which is kind of state-of-the-art, then each of these images has a raw size of 43 megabytes, which translates into more than 500 megabytes per second if we just start to capture the world with 10 images per second, which is not super much, right? In other words, when we continue with that 10 frames per second capturing of the whole world around us, we end up with something like 36 terabytes of data captured per day. Of course, this is really just raw data, but you can probably imagine that this is a huge problem to deal with. First question, of course, is what are we going to do with all these terabytes of data? And more importantly, of course, we are not just into collecting all this data. Of course, we want to derive information from it. And even more importantly, when we are talking about autonomous systems, we not only want to understand what is there, but we also want to relate it, which means that we want to be able to search it so that we can find things again, which we have seen before, for instance. These are just one of the few high-level challenges that one faces when dealing with 3D data. And with this, I would like to introduce Eugen to the stage, because he's the expert, and he can give you more information on all these issues.
So we're coming now to the question how to store, to model the data structures, and this is a topic where I particularly work on, and this is actually a current state of the art. It's about the idea how to deal with the data, not about frameworks, and the core concept is to apply volume modeling for our world, as you can see here, for example, this Mario, yeah, and voxel is basically a 3D pixel, like a cube here, and the difference to this approach, which is kind of common in computer graphics, we divide the full world in voxels and represent a surface, which is actually observed by the camera, by interface between negative and positive values. So actually we use each measurement from the camera to set these values, negative and positives, and to represent the surface. Here, as an example, in 3D, you can see positive voxels in green and negative in red, and the surface is between them, is also visualized here correctly. So actually, why do we use this approach? Because it helps us to integrate new measurements really fast without to perform large recomputation of the environment. So every time when a new image arrives from the sensor, this approach helps us to integrate the new information easily. And in order to store it, like tree-based data structures are usually applied. So in this case, an octree, where each voxel is stored only when there is a measurement. So maybe you can think, why should I store something, allocate memory for something which is not being measured? But this is not so trivial, because 4 years ago, we didn't even have this approach to store the data. So using octrees or binary splitting trees, it's kind of in research right now. But whatever. Right now, we're in the situation that where we can store the data using linear memory allocation, and we increase the access time by combining it with the hash tables. So actually, an octree is stored in a hash map, and if we are looking for a specific coordinate, like in the 3D position x, y, z, first of all, we find the corresponding hash entry, the link to the octree, and then we find, by going down the octree, the required cube, like a voxel. And the reason why hash maps are used is when we traverse the full octree, then the complexity of accessing a data point depends on the height, or on the depth of the octree actually. So we reduce it here to 2 or maybe maximum 3 levels and apply the constant search using hash maps. So this is quite efficient, and of course there are some demonstrations, some examples where this is applied. Here you can see a chapel close to Munich, with a resolution of 3 centimeters. A drone, a UAV, was flying around and taking pictures. And this tower, which is not well seen here, is like zoomed in. So you can see the visualized mesh of this, and also what I described, implicit voxel approach, where positive are green and negative are red. And actually the structure in between them is shown here as a surface, like it's common for computer graphic for rendering with OpenGL. The same technology is being applied for mapping from a vehicle. This is a test run from Braunschweig, where the stereo system was mounted on a car and was mapping streets along the travel path. Okay, so what do we have now by introducing this technique? Right now we can access voxel by 0.4 microseconds. This enables us to model to integrate the new measurements with a speed of 2 frames per second using this small resolution. So actually that's not so much. And in order to be able to deploy these technologies to some realistic scenarios, we would like to achieve like 40 nanoseconds of access time. And generation of meshes for visualization, what I showed you in the slide before from the chapel, is also another issue. I mean, there are approaches, but they are still not scalable in order to be used in production. And object recognition is actually next logic topic, but it's very application dependent and yeah, not covered here. Okay, so in summary, we have this Octree implicit voxel modeling framework, and it enables us to represent a very efficient 3D model, and also the storage requirement is not so high. So actually for 100 times 100 meters plane of 3 centimeters, we would only require 70 megabyte. Yeah, as a conclusion to the whole stuff, today we are able to reconstruct a 3D environment from images using algorithms and state-of-the-art computer vision techniques. But it is extremely challenging, and the infrastructure which is actually required to take the value out of the results doesn't exist. So we have no standards here, no providers, and there are only a few internal solutions in some companies which mainly work on computer vision, and in order to present the results, some faster hacking solutions are developed just to present it's for showcases. And from our opinion is that the 3D digitalization with mobile systems is today in a state like yeah, the web in the 90s. So I guess there is much more to come, and yeah, you are welcome for a discussion of your ideas. How would you maybe approach this issue, these problems with large data? And yeah, thank you.